Okay, let's start. So, Simon is abroad, so I'll do that happily. You all know her. Today we have Carynelisa from here, and she was teaching for 3 hours now, so now it's the first hour. I hope you will make it. Thanks. So please go on.
Okay. So today I'm going to try to squeeze in a description of 2 different subjects. Let's see if I can do it. Of course, you can ask questions if there's something to clarify, but deeper questions wait till the end so I can get through all the good stuff. I'll mention from the outset that I'm talking about work of quite a few people that I collaborated with. Master's work of Idan Cohen and Roby Hartz, an undergraduate guided research project of Hili Kurtzu, and collaborative work with Professor Yoel Yair. I'll also include some work from a summer internship of Shana Rothstein. Okay, so the first part I'm going to talk about the propagation of light in clouds. And here's a typical scene of a cloud. Actually, it's a good day to be talking about light in clouds. We can see that there's a lot of different levels of brightness here, from very dark patches to quite bright patches, even within the same scene of even just one cloud. And it depends, of course, on where the sun is located and where we are located in terms of what light comes out at which angle. And why is this an important problem? I put in parentheses to remember Guy Dagan's colloquial talk. He talked about Earth not as the blue planet, but as the white planet, because actually clouds reflect a lot of light. And we can see here schematically, if we look at the clouds, reflection by clouds, it's something like 20% of the incoming light. So we need to understand this 20% of the energy that's being reflected by clouds back out, and of course that influences how much light energy hits the surface. So why is this a difficult problem? Well, macroscopically, we have to figure out how the light interacts with a whole collection of drops at once. And this depends on what angle the light is coming in from and where we're putting our detector, whether it's just our eyes or a detector in space or on the Earth's surface. And microscopically, we have a lot of different separate events that look like this. We'll have incoming light that I can describe by using the term light, or a light wave, or an electromagnetic wave, or a photon. These are all synonymous. And sometimes some of the light will just continue through straight without encountering a drop. Sometimes it'll hit one drop and then go off to the direction of observation. Sometimes it'll hit one drop and then another drop and then go off to the observation. Sometimes one drop, a second drop, a third drop. And sometimes you can even get with this kind of looping where light will hit one drop, that'll go scattered onto another drop, and then scattered back to the first drop, and then off to the direction of observation. And we somehow have to account for all these interactions. Now, we can actually do a single drop fairly easily. I put easily in quotes. We'll see why in a moment. Because the theory to describe scattering of light by one single spherical scatterer has been known since 1908. It was a solution presented by Gustav Mie. And it took some decades, but by the early 1980s, we had stable computer algorithms that could do the calculation for us. And it can do it for pretty much any spherical scatterer, any size, any refractive index that we want, stably. So that's a very good tool that we've had for decades. And this comes under what's called Mie scattering, or the classical Lorentz-Mie theory. And just a taste of what it looks like. The solution that Gustav Mie presented is something like this. We have a spherical scatterer. It's very convenient to use spherical coordinates. And we have an incoming wave, and inside this electromagnetic wave is an electric field that varies in time and space, something like this. So it's a wave, and it's propagating through the drop. And the reason I drew it like this is because we can see that even from point to point within the drop, the value, the absolute value of the field is going to change, even at a given moment. A given moment in time, this part of the drop feels a different value of the electric field than this part, than this part, than this part, than this part. Throughout the drop, even in one instant, the drop will feel all different values of the electric field. And this is what makes the problem difficult to begin with. But again, Gustav Mie solved it. We don't have to solve it again. He solved it, and we have the solution. The solution looks something like this. So it's actually quite fun. We have inside of these expressions associated Legendre polynomials and spherical Bessel and Hankel functions. It really is a lot of fun. This is what it looks like. We have the solution for the amplitude of the electric field that has been scattered with two polarizations. These are these expressions. And inside, we see we have actually infinite sum, an infinite series, which we have to handle, and it contains coefficients, this little AL and this little BL, which look very innocent, but actually their values are these. Okay, so the solution was not easy. Okay, but again, it's been solved, and we have algorithms that will do this calculation for us. We don't have to reinvent the wheel. We already have this tool. And what we can get out of it is something called the scattering phase function. And the scattering phase function actually looks like this. And what we have here is light comes in from left to right, so we have a light wave propagating, and our spherical scatterer is here in this diagram. And this red line is the outline of the intensity of scattered radiation. So we have some radiation scattered forward, and then we have all around the drop scattered light going out in all directions with this level of intensity. So it's the envelope, essentially, of the intensity values. And we can see there's a lot of structure to it. We have most going forward. Oh, I didn't mention this is actually a logarithmic scale, so we really do have orders of magnitude more going forward than in any other direction. But immediately we have a minimum and another maximum, a minimum, maximum. We have this very interesting structure that will change depending on the composition and the size of our drop. But we can get this for every single drop and every single wavelength we like. We put it into this symbol here, P for phase function. And what we have is essentially the intensity as a function of scattering angle. And the scattering angle is the angle relative to this direction, relative to the forward direction. So we can describe this function as a function of angle, going from 0, which is straight forward, to 180 degrees, which is straight backward. And we can get a value for all of these ups and downs in the intensity, and that's all inside of this scattering phase function. Okay, that's all good and well if we have just one drop, but again, we don't have just one drop. We have all these drops. And so the question is, how can we deal with multiple scattering? Not single scattering by a single drop, but the interactions of the radiation with all of these drops simultaneously. And for that, we also have an answer. The answer is called radiative transfer theory. This has been used for decades, really going back even to 1890s. The official equation of radiative transfer, which anyone who has taken my radiative transfer course knows all too well, or wants to forget, looks something like this. I copied it from Wikipedia. It's actually a continuity equation for a photon gas, so it actually resembles a continuity equation, but what makes it quite difficult is that it's integro-differential. Okay, so we have the derivative of the intensity that we're trying to solve for, the intensity, but we also have the intensity in an integral on the other side of the equation. Now, as complicated as this equation is, it turns out it's not 100% accurate. It's actually phenomenological and approximate. Some work over decades by Yushchenko, who unfortunately passed away a few years ago, really worked a lot on formalizing why it's approximate. Why is it not exact? And I've summarized it here from his paper. First of all, it's microscopically far field. That means it implicitly assumes that drops are quite separated from one another in the cloud. Second of all, it ignores the cycling back. Where do we just see the cycling back? In this picture. It ignores any event like this, where light can be scattered from I to J and then back from J to I. It neglects that. Ergodicity I'm going to not talk too much about because I also assume it, but it's actually an assumption that you can replace averaging over time by averaging over particle positions. The last two are, where are the drops located? Where are the scatterers located? And the theory of radiative transfer actually assumes statistical independence. Positions and states are statistically independent, and that the spatial distribution is random. Now, all of these assumptions are implicit in this theory, but that nevertheless everyone has used for decades, not just in clouds, but in the atmosphere in general, and not just in Earth's atmosphere, but in astrophysics. This is the equation that people use to solve radiative transfer. I'll say a few words about these assumptions, starting with the microscopically far field. Is that even a good enough assumption for a cloud? Well, the mathematical statement of far field is we have 2 pi times the distance divided by the wavelength, and that fraction has to be much greater than 1. And we can check, is that reasonable for cloud drops? And if we do the calculation, by the way, this comes from Roby Hartz's master's thesis, it seems like it would. Distances are in the range of thousands to tens of thousands. The sizes of the drops are something like 1 to 30 microns. If we do the calculation, it really is much greater than 1. Mathematically, it seems that that should be true. On the other hand, if we do a calculation where we don't just use the far field, we include what's called the near field, we find there could be quite large differences, even at those distances. How large? Even a factor of 2.8. A factor of 2.8 difference between the far field and including the near field in the calculation. That's not negligible. And not only that, the differences remain out to distances of more than 5,000 microns between drops. It's biggest when the drops are close. But even if we're 5,000 microns away, we're talking about a half a micron drop, we still see a difference between adding the near field and assuming there's only far field interaction. Okay, what about no cycling back? Again, Mishchenko claimed that that's probably not so important, this cycling back, the fact that radiation can go back and forth between drops before going off to the direction of measurement. But he never actually performed a full calculation, and I'll explain why. Before I explain why, I'll just talk a minute about the statistical independence and random spatial distribution. Is that assumption good? Actually, it's been shown that no. It turns out that cloud drops form spatially correlated clusters. They cluster inside of clouds in a spatially correlated way. That assumption isn't correct. And not just one study has shown that, but a number of studies. This is the most recent of those studies, using airborne digital holography showing these spatially correlated clusters. So that assumption in radiative transfer theory is not correct. Okay, so can we construct a more exact theory? Can we not use radiative transfer theory? Can we solve it exactly? So when I embarked on answering this question, I took a look at what tools do we have already. And there are quite a number of tools that can solve the coupled problem, where we have more than one scatterer at the same time in the same domain. And really, the coupling, the full multiple scattering, these are just 4 such tools that are in prominent use. Okay, so these have been developed, they're well known, and they have been applied, but not to clouds. They've been applied to other systems. It turns out they don't work well on clouds. Why not? Well, the drops are too large. Those methods work well if the scatterers are small. Also, the spacing between the drops is too sparse. To solve using these methods, we need much too much computer memory. Even these days, we don't have the memory to handle it. And numerically, the simulations go into what Daniel Makowski described as unknown numerical territory. And I tested it, and it really does go off into some unknown numerical territory that doesn't represent reality at all. And even Mishchenko himself wrote that all of these techniques are not yet suitable for describing a cloud. So here's, according to the title of my talk, 2 crazy ideas. Here's crazy idea number 1. Can we take the solution we already have from Gustav Mee that we've been using for decades on a single drop and use it for all the drops in a cloud? Okay, so I gave it a shot, and I called this the sparsely spaced spherical scatterer scheme. Not easy to say, but that's exactly what it is. And it bears some resemblance to one of the models, MS3M, because it's based directly on a direct solution of Maxwell's equations, but on all of the drops at once. And how do we do it? we use an order of scattering manner. In other words, the radiation comes in from the sun and hits a drop. From that drop, it goes off to another drop. From the second drop, off to the third drop. And by orders of scattering, 0th order, 1st order, 2nd order, 3rd order, it keeps going until it converges. Here schematically, of course, you have to get all the terms right. Here's the first drop. Here's the second drop. So I take the solution we have. Again, since the 1980s, we've had this solution that's stable. And I apply it to this drop. I know exactly how much, what's the electric field of radiation from this drop onto this drop. It becomes the new incident field. Then I apply the solution again, but I have to turn my coordinate system because now the incident field is going this way. Okay? But I have the solution, right? So I have the new incident wave. It hits this drop and then goes off to the next drop, and so on and so forth. So the only challenge is rotating properly from one drop to the next and summing over all the drops. In fact, it's even simpler than MSTM. I won't go into the details, but conceptually it even works quite in a more simpler way than MSTM. The advantages are, well, first of all, it's the only model that can do this. There is no other model that can describe radiative transfer in a cloud solving Maxwell's equations. The computer memory is literally dependent on the total number of drops. That can be a problem if you get too many drops, but we know exactly how much memory we're going to need. It's readily amenable to parallel computer processing, so we can do the orders spread over as many CPUs as we have. Convergence happens pretty quickly, within 50 orders of scattering, but even sometimes only 1 or 2 orders is enough, and we already have a converged solution. And then once we have a converged solution, we have a sort of multiple scattering phase function. We have the intensity coming out of the cloud due to scattering by the drops in every direction that could interest us. Okay, so this is just a reminder. We'll have a picture like this, but not from one drop, from all the drops at once. So after building it, of course, we wanted to validate it. So I validated it against models that exist, but I couldn't do it on a real cloud. I had to do it on a much smaller cloud where those models work. And just some graphs showing that the curves of the SSSS fall so closely on the other models. For these small clusters, you can't even see that there's more than one curve. But it exactly reproduces results of one model, and these two reproduce the results of another model, again, when the drops are close together and not like a real cloud. Now let's test it on real clouds, or getting closer to real clouds. So we built different volumes of cloud drops of different scales. Some of them are what are called monodispersed, all the drops are the same size, and some are polydispersed, where we have different drop sizes like we have in a real cloud. They look something like this. So here's one cloud volume, monodispersed, all the drops the same size. And here's another cloud volume, polydispersed, where each drop gets its own size from a distribution. And we can run the model and get the results, and we see something like this. This has, on the x-axis, the scattering angle. So 0 degrees is directly forward, 180 degrees is directly backward. And what we're getting is the full solution for the different clouds. And we see that quite a bit of energy is scattered in the direct forward direction. Well, we saw that even for just one drop, right? Just one drop looks like this. And it turns out we had more and more drops, that forward scattering just grows more and more and more. There's a sort of, sorry, after three hours of teaching, a sort of constructive interference going on in the forward direction that keeps growing that energy in the forward direction. I included this slide just to show that I really am computing it in 3D. So if I were to use something that's just one drop, or I didn't account for 3D, the spread of the energy would look something like this, symmetrical, of course. And this is what I get from my calculation on one specific cloud, and looking from above. So looking down on the cloud from above, and you can see that I'm describing energy to each direction in 3D. And it's not symmetric when you're describing a real cloud. And I have similar results for a polydispersed cloud. So I have various polydispersed clouds. And again, we see this strengthening, this constructive interference in the exact forward direction. Now, interestingly, I was not the first person to stumble on this constructive interference. This is some work by Voigt et al. They used one of the other models, GMM, not on such a big cloud, not on a cloud of water drops like I did, but on a cluster, on enough scatterers. And they also found this very strong constructive interference, a lot of scattering into the forward direction. Interestingly, in their conclusions, they wrote, yeah, that's interesting but not important. And I thought, that's the most important thing here. I don't know why they concluded it's interesting but not important. And I see the same thing, just on a much bigger actual water cloud. And we can see how important that is in this table here. What I'm showing you here is the reflectance from the cloud. So how much energy is being reflected by the cloud back up to space. Okay? And we have two columns. The first column I've titled Delta Eddington. This is the approximation to radiative transfer theory in almost every model. Climate models, weather prediction models, general circulation models. This is the solution that they have in their model, okay, from radiative transfer theory. And this is my scheme. And for the 8 clouds I chose. And what we can see here is there's quite a difference. 10 to the minus 5 versus 10 to the minus 11. 6 orders of magnitude difference between the exact solution and the solution used in most models. Now I have to say that all of these clouds are small cloud volumes. This is not yet a huge cloud, like a kilometer-sized cloud, but each little volume can have orders of magnitude different reflectance back to space using the exact solution versus what's typically used in every model that we run. Okay, as part of the title I said not just 2 crazy ideas and 2 new models, but also 2 new developments. So here is the first new development, adding the near field. So actually what I showed here, okay, as complicated as it was to build the model that produced this, I didn't even include the near field yet. And that was the work of Roby Hartz, my master's student. This is the equation that I used in my SSSS model. And this is what it would look like accounting for the near field. So the idea was, let's add in all the terms. If we can already do this, why don't we add all the terms and get the full field? Okay, again, essentially we're playing with the same polynomials and spherical, Bessel, and Yankel functions in these solutions. And again, this is the factor 2.8 that Roby found. That was on a single drop. What happens when we do a whole cloud? So when we do a whole cloud, what we have here is the difference in reflectance, just adding the near field. Okay, that's just between my original SSSS and including the near field. And we find a fractional difference, a relative difference of 0.02 with a negative sign. That means the clouds are less reflective by 2.5%. Okay? 2 or 2.5% less reflective when we include the near field. I'll mention one other new development. I call this new development number 1B. 4 months I've been working on just another feature, which is describing the scattered wavefronts as spherical and not planar. I think of 6 or 7 months I've been working on it. I finally, after all that time, got to this result, and I'm comparing again to another model. Let's see if it works. The green is the other model, the red is my model. It's not bad. These are different angles that I'm looking at against forward scattering and backward scattering. I don't do so bad. But what's interesting is if I go back to the model that Roby's running, it does even better. I went to the trouble of working for 7 months to describe spherical wavefronts, and there's some patches that aren't 100%. And look at the model that Roby's been running. It's even a little better. So it's not even worth it to add the spherical wavefronts, it turns out. Okay, so what conclusions do we have from this part? Well, we can calculate multiple scattering by a water cloud based on a direct solution to Maxwell's equations. It's feasible for small cloud volumes. We haven't scaled it up yet. We don't have kilometer by kilometer by kilometer clouds. But we can do it. We know how to do it, and we have to figure out a better way to scale it up. We found, as I mentioned, up to 5 to 6 orders of magnitude difference in reflectance between the direct solution, the original SSSS, and the conventional solution that's used in models today. And just adding the near field in contributes an additional 2.5% difference in the cloud reflectance. And all of this has implications for the fringes of clouds. Ilan Koren works a lot on that. Probably Tom gave a talk talking about that. Where does the cloud end and the clean atmosphere begin? And there's actually a lot of space where there's these fringes of clouds, and it's not really clear air yet. So the small cloud volumes are exactly that, exactly the reflectance of those patches. There's also a phenomenon called the cloud absorption anomaly that's been around for decades, and some people claim it's not an anomaly, some people do, where clouds appear to absorb too much. But why do they appear to absorb too much? Because they measure flux reflected and flux transmitted through. So if they're getting, and then comparing to calculations. If the calculations are off of reflectance, then they're misestimating this absorption. Maybe part of their misestimation is they're not actually calculating the reflectance correctly. And then in general, when we run these global models, not only do we take radiative transfer theory, non-exact theory, we do a kind of tuning. And radiation balance is controlled primarily by tuning the cloud-related parameters. Of all the parameters we have in these global models, it's the cloud-related parameters that we tune the most, that most affect the radiation balance. And some of the tuning has to do with, well, we're using this radiative transfer theory. It's not exact, maybe. We haven't gone to that stage, but maybe correcting the theory can get us closer. We can do less tuning of our models. And of course, in general, just going back to this initial schematic picture I talked about, again, if 20% of radiation that comes from the sun is reflected back to space, and we're doing corrections of sometimes 5 to 6 orders of magnitude, or even 2%, well, 2% of the 20% is still a lot. It still could be a lot in terms of climate, right? So, so it has a lot of important implications. I should have said that a little bit stronger. A lot of important implications on the climate from this work. Okay, so part 2. I'm still going to be talking about light and clouds, but now a different kind of light. So this is actually anyone who came to Professor Yoel Be'ir's talk in the CAO seminar. He talked about observations of these phenomena called transient luminous events. And these transient luminous events are sort of like lightning, but way up in the upper atmosphere. So in this picture, we have lightning that we're used to in the troposphere down here. And it turns out, shortly after a lightning event, we can get another flash of light way up in the upper atmosphere, in the mesosphere. And these are called transient luminous events. They come in different shapes and different colors, because different molecules do the emitting. And they look like this, and they have fun names. So we have things called sprites. This is a carrot sprite, columniform sprite, jets, gnomes, pixies, elves, halos. They had a lot of fun with naming these things. I'm going to focus on sprites. So sprites like this or like this. And this is what it looks like actually photographing a sprite. So what you need to do is wait for a storm to come through, and then find a place where you can aim your camera up way over the storm into the mesosphere and take a shot instantly after the lightning. Usually this is done at night. And we've actually done this here in the Institute of Earth Sciences. One of my master students who's now doing a doctorate here, Elia Kubatislavsky, he took a camera at night and went and, it's called sprite hunting. He hunted sprites and took photographs like this. So one thing we do when we're trying to study these sprites is to try to photograph them and measure the field. And the other thing we want to do is understand the physics behind it. So why is it important? Well, they involve fundamental exchanges of energy between the lower atmosphere and the upper atmosphere, or the atmosphere and the ionosphere. And if we can understand why they happen and how they happen, how big they are, we can understand better the global electric circuit, ionization processes in the mesosphere, conductivity, even plasma processes. It can contribute to our understanding of plasmas in general. And of course, electrodynamics during storms in general, because we need the lightning flash first, and then we get the TLE above it. A little bit of a history. The person who actually predicted these flashes was C.T.R. Wilson, and we're going back to 1960, 1924. where just on the basis of some initial calculations decided, or not decided, worked out that maybe the electric field in the mesosphere could grow large enough to exceed the threshold for breakdown. So he hadn't seen it, he just thought, oh, let me calculate the electric field in the mesosphere. I think sometimes it's going to be high enough to cause electric breakdown there. How high is the mesosphere? We're talking about 60, 70, 80, 90 kilometers altitude. So he predicted it. Initially, some of discharges were reported by aircraft pilots, but they were discounted. People thought they were just dreaming it. The first recording was in 1989, and then we started getting models trying to predict it, trying to understand it also in the 1990s, shortly thereafter. A little more of the history. One of the groups that really worked on this a lot was the group of Haspel et al. And they built the first simple models to try to predict the electric field in the mesosphere and see if it goes past the breakdown threshold. And essentially, he just took two equations. One is the calculation of the electric field in a static way, using Poisson's equation. And the other is letting free charges move by using the continuity equation, continuity of charge. And another thing that he did was prescribe the buildup of charge in the cloud. Okay, so we need to describe why we're getting charges in the cloud to initiate the lightning, and then once the lightning starts, to calculate the field above the cloud. So he had a prescription that looks like this as a function of time, where positive charges and negative charges are starting to separate from one another. They're growing, growing, growing in absolute value, and then a lightning will hit. So here's the point where the lightning hits, okay, in either one. And then let's calculate the field that we get once the lightning starts. Now, in these first models, he and his group assumed axial symmetry. In other words, they described an atmospheric column like this, as a cylinder. The cloud is lined up in the center of the cylinder. We have the positive charge and the negative charge. The lightning will drop one of these charges to the ground. And we want to calculate the electric field in this domain. And why did he choose axial symmetry? Because it reduces it to just two variables. Instead of a full three-dimensional problem, now we have just two variables to work with. And when you try to solve the equations, especially if you use finite differencing, it's easier with two variables than three. But not only Haspel back in 1995, year after year after year, everybody kept continuing with the cylindrical symmetry, with the axial symmetry and cylindrical coordinates, two variables only, for the same reason. You only need two variables to solve in your equation. So you can see all of these papers and on, I didn't even list them all, continued with the axial symmetry. Why? Well, I already answered. Number one, it's fairly okay if you have a symmetrical cloud, but also they just couldn't do any better. So I quoted here, the choice is related to the need for a large simulation domain and a very fine time resolution. Trying to do 3D involves a computational time that currently can't be done. That was back in 2010. But it does prohibit us from describing scenes like this. So sometimes we have multiple clouds and multiple stages. Lightning happens in one and then another. Not everything is symmetric. So there was a need to build something that could describe lack of symmetry. So this is one reason, neighboring cloud cells. Another reason is sometimes these sprites have been observed to be offset from the parent lightning. So the lightning's here and the sprite is way off there. And that breaks the symmetry, and they didn't understand why that happens. So here's crazy idea number 2. Build a 3D quasi-electrostatic model that doesn't use finite differencing in space. In other words, it's more stable, more practical when you have such a large domain, time stepping, okay, and you want it to be stable. And where did I pull the idea from? Going way back to classical electrostatics, not even electrodynamics, classical electrostatics, the method of images. So the method of images, anyone who studied classical electrostatics probably learned this. You can use image charges to enforce a zero potential on a boundary. Okay? So people do this as undergraduates, first year, second year of physics. My idea, which was a little different, was not to do it once on one charge, but to take every charge in the entire atmosphere around this storm and use the method of images. Okay? So every charge that comes in and out that flows due to the field that the lightning causes, every charge will get an image. Okay? So I'm using a whole domain of charges and images. The advantage is it's actually an analytical solution. It's an analytical solution. You don't need finite differencing. And it's even a little more complicated because the surface of the Earth is approximately at zero potential, but also the boundary of the ionosphere is at zero potential. We have two boundaries. But even two boundaries is well known. What I've copied here is somebody's physics lecture where they were showing how to describe two boundaries in physics with image charges. So you just need to add enough image charges, and you keep adding more and more image charges each time to preserve the zero potential on both boundaries. So this is literally from somebody's lecture, somebody's homework assignment, okay, where he says, in a funny way, it's turtles all the way. So I copied the turtles. Anyway, it looks like this. You have one boundary and another boundary. Here is the one initial real charge. And then you start putting an image here, but then you need an image here, and then you need an image here, and then you need an image here, and you keep going. And it's actually an infinite series, but of course, the charges are getting farther and farther away from the domain. So at some point, you can cut it and say, okay, that's enough images, we can stop. Okay, so that's what I do. I let the charges, free charges flow just like Pascal did. That I kept as he did. We need to describe the conductivity of the atmosphere. I used the same expressions he did. So that is another aspect. And actually this, just adding the free charges, is the only finite differencing at all, for those who know finite differencing. And it's finite differencing in time and not in space. There's no finite differencing in space. Okay, a lot of advantages. I won't go through all of this because I think everyone's getting a little tired, but I'll just show one of the advantages is it's relatively insensitive to the horizontal extent of the domain. I can squeeze the domain from 60 to 40 kilometers, and I get the same result. If I squeeze it too much, if I make it only 20 kilometers, we start to see a little bit of difference. But because I'm not artificially prescribing some boundary condition due to finite differencing on the sides of the domain, I don't have any boundary condition on the sides of my domain, I can make it much more compact than other people's models. I can also use a relatively large time step. This is larger than what most people do. Okay? It's still small, it's 0.0001 seconds. But it's larger than what other people do when they have finite differencing. Okay? And we can see it gives the same result even as an order of magnitude smaller time step. Validation. So let me validate against Pascal's work from the 1995, 1997. Here are his original plots of the vertical profile of charge density and the electric field. And the moment where you get a sprite is this curve here. This line is the breakdown field. And this curve is the new electric field due to the lightning event. And you can see this blip here. It surpasses the breakdown field right here at this moment, 0.501 seconds. That's where sprite's going to be in his model. Here's my model. I get the same curves. And not only the same curves, but this is still 2D. I can show in 3D the field and the charge density at every point. Now, let's move on from validation to some new results. I want multiple cloud cells. Here's just one cloud cell. And what I'm showing here is a series of time steps. And anywhere we have this contour of 0 is where a sprite can occur. That's where the field surpassed the breakdown field. You can see right here, a moment after the lightning starts, the lightning is going to start at 0.5 seconds, we start to get an area where a sprite can form, and it evolves a little bit over time. That's one cloud cell. Now I add a second cloud cell. I can offset it in space, I can offset it in time, and I start to get areas that look like this. They're not symmetric, they're bigger, they vary in time in a different way, and this kind of simulation only my model can do because I have now a 3D model. Okay, not just 3D, but stable for almost any parameter set. I can also now break the symmetry immediately by describing wind shear in the cloud. So I take a cloud, and the cloud is no longer symmetric about the z-axis. The cloud itself is tilted. There's wind shear. And you can see I get a tilting of the charges. I get a tilting of the electric field. I can move my, strengthen the wind shear by more and more and more, and then see where the sprite could be. And this area of the sprite shifts together with the wind shear. And again, this is a completely 3D effect that no other model can describe. Another thing I added, so this is, I said, new development. So a new development is adding a time-dependent conductivity. The conductivity is now no longer constant in time, but changes based on the electric field, which moves the charges. You move the charges, you change the conductivity. So there's a nonlinear feedback. And then, using that new nonlinear feedback on the conductivity, I also looked at interesting charge time dependence patterns. So not just one smooth discharge in the lightning, but things that jump, fits and starts, we called it. And I just can describe not only the 3D effects, but delays in sprites due to this, these more interesting lightning patterns in time. And we can use this. For this, I needed to collaborate with Javier, who has all the observations. We could predict, or we can simulate or recreate inception of a sprite that's delayed by more than half a second from the lightning. It's the first time that anyone was able to reproduce that effect. Here's the actual event, okay, as seen from space. And here's my reproduction, and I start to get an area of the sprite at the same tenth of millisecond that they found in the observations. And here's another very special event where the sprite, this is the sprite, and here's the lightning was down here. This is the sprite itself, and this is a second lightning event that was off to the side. So I was able, because I have a 3D model, I could simulate this. This was the longest delay ever observed. It was almost a full second delay. Lightning, and then a full second later, the sprite appeared. So this is something we submitted to Geophysical Research Letters, and I was able to simulate it. So here's the beginning of the sprite in my model at the exact same time that they observed from the space station. And I did for just the single lightning event here, and also for this one offset, the two of them together. So I did all the possible simulations, and every configuration was able to reproduce this 1 second, or just about 1 second delay. And then just one more new development. So this is the last of the new things. All of this actually was still, because I was using the image charges, electrostatic into what's called quasi-static, okay? Because the charges do move. There's a continuity equation, the charges move in response to the field. But it's still called quasi-static, and I thought, can I move it to dynamic? Can I make it fully dynamic? So what I did was, I took what's called Jeffimenko's equation, and I added to the Coulomb force velocity. In other words, every time charges move from one grid to another, one grid cell to another, I calculate a velocity, and that velocity in and of itself adds to the field. So I do that for every grid box, every time step, I add the velocity. Not only did I add the velocity, but because I'm already moving into dynamics, I made it causal. In other words, the signal from an electric field in one point takes time to get to the upper atmosphere. Okay, it travels at the speed of light. It's pretty fast, but it's not immediate. So I calculate every single point, how long does it take the change in the field to propagate to some grid box way up in the mesosphere. So everything is now fully causal, and the velocity is incorporated. Velocity of the charges is incorporated, and here's the new result. The old result is this blue curve. The new result is the orange one. And we see causality, first of all, delays the start of the sprite. Again, the sprite is within the contours. Delays it by 2 time steps, but also enlarges it tremendously. It gets much bigger because it built up more until the sprite actually started. And it continues on and on and on for much longer time than without including causality, without including the velocity field. And another interesting effect that I've been looking at for a couple months is that it seems to oscillate. So we have the growth, okay, but then it decays. Here it's smaller, increases again. Here it's 0, increases again. Increases, decreases. 0, increases again. We're getting damped oscillations of the sprite area with time. To the best of my knowledge, it's the first time anyone has shown these damped oscillations. It's kind of an inertia effect. It's an overshoot and return due to the time lag, plus maybe some ringing because the impulse from the lightning hits the ionosphere and reflects back. So this is the first time that's been shown, and this can also help explain why you might get a delay. You might get a sprite right here, all these time steps after the lightning started, just due to this. I haven't added any other effects. It's a damped oscillation that comes just from the causality and the fact that I've added the velocity term to the equation for the field. Okay, so conclusions from this part. We can use the method of images from classical electrostatics, first year, second year physics, to conduct quasi-electrostatic simulations in full 3 dimensions with no time finite differencing in space. And it's a robust method because it's based on an analytical solution. Any thundercloud charge distribution can be described fully in 3 dimensions. And we can use this to explain all kinds of interesting phenomena. The appearance of sprites that are quite far from the parent thunderclouds, and long delay times between the parent thunderstorm and the appearance of the sprite. Now, over the years, people saw these observations and invoked all kinds of other mechanisms to try to explain why is the sprite way over there, and some milliseconds after the original lightning event. And I don't need any of those other explanations. I don't need to invoke all these inhomogeneities or meteors or detachment of electrons, all these kinds of things that they came up with to try to explain it. Actually, the basic physics can explain it if you work in 3D and put in all the terms you need. Okay, that's it.
First of all, fantastic work that fundamentally really pushes the basic science goals. Just a big applause for me. It's great work.
Thank you.
There's 2 questions. One, do you think this reflects on the sort of the too few, too bright problem in cloud models, that low clouds tend to be too bright? There seems to be like, does it reflect onto like these classical problems or basic problems we see in cloud models? And 2, do you think these methods are, especially the first part, is amenable to modern AI methods, like a digital twin of a radiative model? That computationally, is that feasible or is it not?
Okay, so as to the first question, I think yes. I mentioned the cloud absorption anomaly and the tuning cloud parameters, but any fundamental thing that's going on with models where the cloud properties, the radiative properties of the clouds aren't quite right, like the brightening or things like that, it could be applicable. We haven't said, okay, let's try to answer some of these questions yet, but in principle, yes. If the actual reflectance of the cloud is different from what we're using in the models, then yes. We'd like any way possible to take our small cloud volumes and expand it. So if it's by way of AI, great. We haven't really made that progress, but it sounds like a great idea to try. Simulations on as many small cloud volumes as we can, and somehow use AI to help us scale it up.
Can you, thank you for an excellent talk. I learned so much. Is there any idea what causes the damping in your damped oscillator view of the spark? Because you have a decrease in amplitude that's almost measurable in the simulations.
Yeah, so that's one thing I've been looking at for the past 2 months. At first I thought it could be something like the plasma frequency, because it's acting like a plasma, but the plasma frequency is much too short. It's much too for this. So that's why I wrote here is a kind of, the time lag allows the field to build up and it kind of overshoots, like a physical mechanical damped oscillator that overshoots the equilibrium point and then starts oscillating around it in a damped fashion, that it's the field now experiencing this. It overshoots because there's a lag. It's being held back, so I use causality. And then it starts to pile up on that grid space So it grows, but it kind of overshoots the equilibrium value, and then I end up with these oscillations.
In the first part, when you showed the big clouds and the multiple scattering, you always got a minimum at 100 degrees.
Mm-hmm.
Is there any reason? And by the way, the other results you showed by other people did not have this minimum at 100 degrees. Is there any reason for this 100 degrees?
Clouds in general have specific features that tend to turn up over and over again. Some of them we're very familiar with, like the rainbow. So the rainbow comes out at a certain angle because there tends to be constructive interference. No matter which cloud, as long as you have rain, we tend to get the constructive interference. But by the same token that we have this bright band, colorful band, we'll get a minimum, and that minimum tends to turn up at a certain angle. So you can get that in a rain cloud, you can get that in a regular cloud. There are other phenomena, not just the rainbow, there's the fog bow or cloud bow, and there's the halo, and there's the corona, and all of these are pretty constant. They turn up the same angles from cloud to cloud if you have the conditions of the size of the drops correctly. So there are interference effects that somehow work out to stay pretty much at the same angles regardless of exactly where the drops are. Yeah.
Two stupid questions. Regarding these jets or sprites or however you call them, how frequent are they? Do we need a certain threshold for a certain thunderstorm to activate them? This is one question. And the other one is concerning the first part of the talk. Can we make any experiments on artificial cloud or with laser beams or something like that we can actually measure the scatter from, I don't know, cloud that we generate in the lab or something like that?
Yeah, so I'll answer the second question first. Yeah, if we can take a cloud chamber, and if we do the measurements carefully enough, shine a laser through it and measure at every angle, we can try to test this. Yeah.
Has it been done?
It's been done, but not testing my theory. I mean, in general, testing reflection and scattering at different angles with some resolution has been done, yeah. Okay, so going back to the sprites. So you need a strong lightning event. So it's not every single lightning flash. So it's the top 10% in strength of lightning that could cause a sprite. Having said that, there's so much lightning, it's thousands of sprites and jets could be occurring at all times, and we measure just a very tiny fraction with our attempts, whether we're on the roof of a building shining a camera or from space. We can calculate hundreds over time and analyze them, but there are much more. There are thousands going on.
Any questions? If not, so first, thank you again.